Good morning, everybody. So today we are going to be working on expected value. And um, I apologize for the highlighted blue, but I have to remember to change the font when I go to show you the graph. So imagine that we have a population of 10 computers. Notice that this is capital N, not little n. And the reason it's capital N is because it's a population. If we said a sample, it would be little n. Just little things that matter in statistics. And the following list of numbers is the number of defective pixels each monitor has. So there's 10 monitors. The first monitor has no pixelation issues. The second monitor has no pixelation issues. The third monitor has one pixelation issue, and so forth. Now, the mean or the average number of pixels that are damaged will end up being 1.2. Well, let's show you how to get there. And I'm trying to get to the formula that we had the other day. So first of all, if I just add them all up and I divide by how many we have, we're going to get 1.2. But there's another way to view this. We have two zeros, we have five ones, we have two twos, and we have one three. And if you can remember your days of common denominators and fractions, this denominator belongs to each one of these um, multiplications. So this 10 is really 2 times 0 over 10. And this 10 is really, gets moved to 2 times 0 over 10. And this 10 gets moved to 5 times 1 over 10. And 2 times 2 over 10. And then 1 times 3 over 10. Now, you could write it as 2 times 0 over 10, and then 5 times 1 over 10, but that doesn't help us in this situation. We're going to think about it in terms of the chance or the probability of it occurring. Well, 2 out of the 10 times that we're looking at this list, we have 0 pixelation issues. 5 out of the 10, we have 1 pixelation issue. 2 out of the 10, we have 2 pixelation issues, and 1 out of 10, we have 3 pixelation issues. So it's out of order, but the formula that we have, and I'm going to write it up here, forgive me for doing it this way, is mu is equal to the sum of, and so each of the additions that we have. Now, I wrote it px times x, but it's really generally written the x value multiplied by the probability of that x. Now, remember multiplication is commutative. What that means is 3 times 4 is the same as 4 times 3. So this 0 and this 2 tenths, relax a little bit, haha, math joke, is able to be flipped around. So 5 tenths and 1 I can flip around, 2 tenths and 2 I can flip around, and the same thing with 1 tenth and the 3. Now, where this is heading is that we are getting to a thing called the expected value, which is another name for the mean, which is also another name for the average. So sometimes you'll hear people talk about the expected value. You might hear them talk about the mean as well as the average. Now let me click this back to normal typing, and I need to change the font here to a 12, and then I can get my full graph back up. So if I do the probability distribution for my x and my px, well, the random variable x's that could occur would have been 0, 1, 2, or 3. And 0 occurred 2 tenths, 1 occurred 5 tenths, 2 occurred 2 tenths, and 3 occurred 1 tenth. So if I draw the relative frequency histogram, and remembering to label my axes as well as to give a title, I'm going to end up with 0.2. I'm going to end up with 0.5, 0.2, and then 0.1. Now, a few comments. Again, this is relative frequency. These are the outcomes that could occur from the random list of random variables. And then the probability of the pixel damage. You have 2 tenths. So 0.2 is 2/10. You have 5/10. 0.5 is 5/10, and so forth. I have this comment that this is skewed right. Well, it is a little bit. And let me draw in here what I'm looking for, or what I see. I don't know why that's doing that, so hold on one second. Draw. You're not letting me draw. There we go. Click. I'm going to try and use a different color to see if I can get it to sort of show up what I'm trying to highlight here. So if I draw the distribution and I follow the shape of what's going on with the histogram, I have something pulling the mean a little bit to the right. So it's got a bit of skew, not much, but a little bit. And so if I ignored, like just pretend that this cube is not there, or that box is not there, well, the mean would definitely be 1, because this is balanced, and that's the center. And most of the stuff is in the center. So we'd end up with a mean of 1. But this box here is pulling the mean off to the right. The mean is sensitive to things when they're off of the balance. So this is why the mean is 1.2. And that 1.2 is our expected value. All right. Now, I've got another problem for us. Here we go. So gambling. Let me expand this a little bit. I want to highlight, and I want to get this to 16 font. There we go. So a Nevada roulette wheel has 38 pockets, or where the ball lands. It's numbered 1 through 36, and we've got a 0 and a double 0. Now, the 1 through 36 is set up so that half are red and half are black. And the 0 and the double 0 are both green. Now, when you're setting this up, you've got to think about what it is that can occur. You can lose $10 or you can gain $10. And when I say you gain $10, when you win, you get your $10 back and you get an additional $10. So you bet $10 to land on a red. It seems like, and a lot of people think, well, this is a fair game. Fair meaning that half of the time you would win, half of the time you would lose. Well, what we have to consider is the fact that when we bet, and we bet on the red, 20 of the 38 pockets are going to result in a negative 10. We're going to lose our $10. And only 18 of the 38 pockets will we win $10. Will we get our money back that we bet, and we get an additional $10? Well, this is an expected value situation. It's really using the mean. It's really using the average. So we take negative 10 and we multiply that by its probability. Here's our x. Here's our px. This is our random variable. It's our outcome that could occur. It's negative 10. So we have negative 10 times 20 divided by 38. And then we have the 10 that's going to occur 18 out of 38 times. And so this is, give me a second here. Here's our x. Here's our px. And here's our other x. And here is our px. Okay. Now, if you crunch that into your handy-dandy graphing calculator, you're going to get a negative 0.526. And what that means is that you're going to expect to lose more than 52 cents per play. Not fair. Fair would be 0. Half the time you win, half the time you lose. Okay? Well, I'm hopeful that helps a little bit. I know that some of the problems that we are looking at had these types of situations involved, so I hope that makes sense.